General relativity, step by step. I've been fooling around with these equations of state here, which I need to close this system of two equations in three unknowns. I've got these two equations here from the Einstein field equations, nice and simplified. And I've got three unknowns. I've got A, I've got rho, and I've got P. And as I was saying, I could close this system by appealing directly to the Einstein field equations, but that's A, a lot of work and complicated algebra, and B, you miss this nice piece of insight which I'm going to give you in this and the next screencast. Yeah, the Einstein field equations have got built into them the fact that we've got energy, mass, conservation. This thing here is the stress energy tensor, and it's covered in GRSS 93 through 109. It is a complicated and difficult concept, so this is why I'm going through this slowly. You'll remember that when I was using the Einstein field equations, I wasn't just considering it with the Ricci tensor with two upstairs indices, I was considering it mixed with one upstairs and one downstairs index. And so what I want to do is to consider the stress energy tensor itself with one upstairs and one downstairs index. So I'll show you how that works. It's an entirely non-trivial process. So what we've got is T mu nu semicolon nu equals 0, and that's conservation of mass energy. What I'm going to do is take a bracket of this. Actually, it's a vector equation. There are four equations here, so I'm just going to make that clear. And now what I'm going to do is, because I want one upstairs and one downstairs, I'm going to multiply it by the metric tensor mu alpha. And I guess that lowers that index, and the free index is now an alpha down there. Okay, so what do I want to do now? I want to consider the alpha equals the time component. So we've got four equations here, but I'm only interested in one of them. I'm interested in the time evolution. So what that tells me is I've got G mu T open bracket T mu nu semicolon nu equals 0. That's just a single equation. That's just one equation. All I've done is single out the time equation from this genuine tensor equation here. And then I'm going to observe the metric tensor G. Well, I've written it down in different ways, but I'm going to write it down again like this. That was A 0, oh, that's A squared, 0, A squared, Q squared, 0, 0, 0, A squared, Q squared, sine squared theta. Is that right? Where A equals A of t and Q equals Q of r, which was the flatness parameter. However, what I want to observe is that this is diagonal. I've only got terms along the diagonal of this matrix here. And so what that means is that this guy here, the only term I need to consider is this one here, which is a constant. And if it's a constant, I can take it inside the bracket, because we are differentiating here. So what that says is that G mu T, T mu nu, semicolon nu, equals 0. What I've done is I've taken this metric tensor here and I've observed the fact that because it's constant, it can slip inside this bracket. Actually, maybe it would be clearer if I wrote that bracket, if I wrote that bracket there, just to make it absolutely clear what's going on. So what that means is that T nu semicolon nu equals 0. Now, it doesn't look like we've come very far, but we have. We started with this semicolon nu equals 0, and I'm using the fact that one element of my metric tensor is constant, and so that means that I can effectively lower, well, never mind effectively, I can actually lower one of my indices, and so long as I'm only interested in the time component, because this was constant, we've got this nice equation here. Now I'm going to remind you about covariant differentiation. Covariant differentiation. Differentiation. And that was covered in GRSS 034 and 035. I'll just remind you what that is, and then I'll apply it to these guys here. We had a tensor, I'm going to call it X, and it's got an upstairs index, let's say an alpha and a beta, semicolon gamma, and that was equal to, let me see if I can get this right. It's quite tricky to get everything right. So it was di X alpha beta by di little x gamma, that's that gamma there, and there was a plus correction because there was for the upstairs index, and there was a negative correction, a subtraction for the downstairs index. And let's see if I can get this right. Right, now the positive correction was when we summed for the upstairs index, so that turns into, let's say, a pi, and we'll sum there. The negative correction was where we summed downstairs with 1 there. And then, let's see if I can get this right, the alpha was free, which was there. The beta was left alone, and gamma is free. For this term here, what did we have? The alpha was left alone. Yeah, so here you see you sum over the top one and leave the beta alone. Here you sum over the bottom one and leave the top one alone. The only things that we've got left are beta and gamma. So that was covariant differentiation. And what I want to do now is to apply that to this formula here. T nu semicolon nu equals, I'm just going to use the same formula. So it's a little bit harder because I've got an implicit summation. I'll actually write it in. It's as well to write the explicit summation in when you are fooling around with specific elements of your multidimensional tensor. If you've just got an equation like this, I don't even bother writing the summation in here because it's summed over pi here and here. But this isn't a formal tensor equation because of that. Actually, I ought to write it in a different colour just to make it clear, T, that it's not a real index. It's just one component of a genuine vector or genuine tensor equation. So let's do that then. So we've got di T nu T by di X nu. See, what I'm doing is I'm taking this formula here, which I copied down, and I am applying it to here, but I am just doing a straightforward transportation. I've got alpha, which turns into a nu. I've got beta, which I haven't written yet. Oh yes, I have. That beta turns into a red T, that's right. Plus Christoffel symbol. The alpha has turned into a nu. That pi we may as well leave there. Gamma is the differentiation thing, which is nu. Observe that we are maintaining the summation across mu. T, because x was t here, pi, and that beta there was a red T. I'm putting it in red just to remind myself that it's not an index I can sum over. It is a specific element of this equation. Back to black. Minus Christoffel symbol. Summation. That's a red T there. Gamma was nu, wasn't it? And that's times the metric tensor T nu pi. Whew! That's quite a lot of work, isn't it? What is this thing equal to? The whole thing is equal to 0. All right, there it is. Now, we've got an implicit summation across nu and across pi. We're summing over nu here and pi here. Here we're summing over pi there and nu there. However, we can take advantage of the symmetry of the situation because the stress energy tensor with one upstairs and one downstairs index is, I nearly said symmetrical. It's diagonal. So that tells me here that this summation's dead easy. This summation hit this we know that nu must be constrained to be t, because it's only when the two indices match that we've got a non-zero term. I'm pausing there because just the fact that the term is 0 doesn't mean that we can ignore its differentials. It might just be crossing the axis and just, I mean, we might have some sort of curve here, and just because it's 0 doesn't mean that the derivative is 0. But it does in this case because the off-axis elements are identically 0. They're always 0. They're always 0. It's not just a moment in time. That's an identity. So we know that nu equals t, and so we can effect that summation quite easily. Di t and then tt by di t, which is that term there, plus, now this one is, again, we're going to use the fact that the summation on pi is trivial because that's only the one term that we need. So, blanc, I guess I should write it in red. T, these should be in red as well, I guess, because it's just a specific, oh, come on. Not a good advert for OneNote. In red, we've got T and T here, back to black. What am I doing? I'm writing down that, and then that's nu. There's a summation over nu here, which I'll put in there. Sum over nu. Stress energy tensor times pi was now a red t. That's quite nice. Minus. This one's a little bit trickier. This restriction here, because it's diagonal, specifies that pi equals nu. So when I do the summation, there's two summations here. There's an implicit summation in nu and an implicit summation over pi. But I don't really need all that work. I haven't got 16 separate terms because each one is 1, 2, 3, 4. I've only got 4 because I'm only interested in terms where nu equals pi. So I'm going to write my summations a bit more neatly. That's summed over nu is this one. And I've got minus sum over nu again, but it's an odd, well, you'll see, it's an odd term. We've got the the Christoffel symbol here with a red T down there. Now because nu equals pi, I'm just going to use I'm going to use pi for both of them, but actually I'm going to do it in blue. You'll see why, because it's pi, pi, and there's T, back to blue, pi, pi. What I'm doing is I'm writing this expression down here, but with the requirement that nu equals pi. And I'm writing it down in blue because they're all equal. Oh, that's summed over nu, and it should be summed over pi. They're all equal. And so what we're doing is we are summing across nu, but pi appears 1, 2, 3, 4 times in this expression, which is kind of illegal under the Einstein summation convention. You should only be summing in the Einstein summation convention a single upstairs index with the same index written in the downstairs position. And we've got 4 of the stupid things here. So what I'm doing is I'm using non-legal tensor or non-mathematical arguments. I'm using arguments based around the diagonality of the stress energy tensor. And this is why this equation looks peculiar. Is that a plus or a minus? That's a plus, isn't it? The whole thing equals 0. And what I'll do in the next screencast, this one's already gone on far too long. I will evaluate this, this monster in the next screencast. Stop.